Okay, now let me teach you. Okay, first of all, thanks to the organizers for inviting me. It's certainly been a pleasure to be here for a week and hearing all these great talks, and I'll try to pull my weight. Okay, so I'm going to be giving a series of 4 talks, and this is a quick overview. Today, we're going to be doing a lot of math and no calculations. We're going to be converting a model from, first of all, starting with the model, figuring out the master equation, and then converting it 2 more steps till we end up with the field theory. The reason I want to go through this in some detail is that it's actually a very powerful technique that has a lot of applicability. A number of the talks we've heard from some of the student talks could well use this in their model. Then I'm going to follow up with, once you've got the field theory, what's it good for? And we're going to do a complete detailed calculation of Feynman diagrams of the normalization group for the A plus A annihilation reaction that Danny was talking about earlier. So at that point, we'll have done 2 lectures, lots of math, and 1 problem solved. Then we'll sort of follow through with, what's it good for? What kinds of things can we do? I'll try to give you a survey of what has been done so far, though by no means complete. I'll just pick a few highlights, give you the things that I understand the best. And then we'll finish up with an interesting variation that falls into this category of field theories, thing with these active to observed state transitions, which I'll say more about later. Okay, so you've already heard about diffusion-limited reactions this morning. So this is maybe not necessary, but basically we're imagining some kind of a lattice model, particles hopping around on a lattice. If we're doing an A plus A goes to A, then when these 2 meet, they will coalesce into 1 A particle, maybe with some probability, maybe at some rate. And here we can have 2 species of particles, and so these 2 look like they're about to come in an annihilation. And then we have to be careful when we define our model. What's going to happen here? Do we allow both particles to hop on the side? Do we have side restrictions? So there's a lot of variations of these models you have to worry about. And just as a quick example of what comes out of these kinds of models, and again, this has all been alluded to earlier, is that for this particular reaction, if the dimension is high enough, rate equations are valid, and you get the 1 over t to k, and you get a non-universal exponent. And next time I'll talk a little bit about where that non-universality comes from. But when you reach 2 dimensions and below, well, first of all, below 2 dimensions, you get this t to the minus t over 2 that Donnie was talking about. And at 2 dimensions, well, these exponents match, and so you get the 1 over t, but you get a log correction. And then what's striking is that these coefficients are universal numbers. And that's one of the things we're going to be trying to show. We're going to try to show where do these sort of, the exponent change at 2 dimensions, where does that come from, and what is the origin of the universality? And can we calculate those numbers? Okay, so you can kind of see the whole outline here. We're going to be doing it in 3 steps today, getting to the field theory. First, we're going to practice a little with master equations. And we'll get to the master equation for the full reaction diffusion model. And then we'll map it to the Doi representation. It's sort of a quantum mechanic-like representation for a classical model, which is a little exotic, maybe. And then how to turn that into a field theory. Okay, so early slides probably can go through fairly quickly. What we imagine is we've got some lattice, so I have some discrete values. We have some occupation numbers of some particles on each lattice. And then let alpha denote a state. So it's a full configuration information, right? Alpha means I know exactly how many particles are on each lattice. Sorry. And then the fundamental quantity that defines our model, basically, or that we'd like to solve for in our model, I should say, is the probability of obtaining state alpha at time t. And we've seen all this before, too. We write down our dynamics in terms of the master equation. These transition rates from some state alpha to some state beta, whether that be a hop or a decay or an annihilation, that defines our model. So specifying what these W's are is where we pick our model. Then we just throw it into the master equation. We've got a gain and a loss term. I don't think I need to go into that too much. I do want to make 2 observations. One is that doesn't matter what you choose for the rates, detail balance, 0 rates in certain directions, doesn't matter. You're guaranteed to preserve probability by construction. Basically why we set it up that way. And then the second thing is that, of course, it's first order in time, so we do need initial conditions, but no more. and then we have a well-defined solution. All right, so let's practice a little here. Simplest thing we can do, we've got one lattice site, 0 dimensions. Right? One lattice site, we're going to do plain old exponential decay. Now the key point here is I want to have identical particles on the site. Okay? So the rate of a transition from n particles to m particles, first of all, it can only go down 1. So it's 0 unless I'm talking about taking one step down. But then, and here's the key point, it comes in with this factor of n. If I have 100 particles, each acting independently, I'm going to get a faster decay than if I had 10 particles, each acting independently, right? So I need to have that factor of n in there to represent that any one of those particles could have done it. So when we put that in the master equation, here's our gain term. We start from a probability of one higher occupation. A decay happens, it brings us into state n. But we also have a loss term. All right? So there it is. That's exponential decay. But you say, wait a minute, that doesn't look like exponential decay. What's going on? Well, let's show how you get back to what everybody knows of as exponential decay. What you want to talk about is an average number of particles. So we define that average to mean sum over all possible ends with the probability. And now let me write down a time derivative for this average. Well, the time derivative only acts on the probability. So now I've got a p dot and I can throw the master equation in. It's just the same master equation from before. Okay. Then, okay, first step was just multiply out everything. Nothing there. Next step, we do a variable shift. Not in the second term, but here in the first term. We let m be n plus 1. So here it is, it's just m. This n plus 1 goes to m. This n goes to m minus 1. And now technically this sum was over n going from 0 to infinity, so this should be from 1 to infinity. But it doesn't matter. I can make it 0 to infinity because there's nothing there anyway. And now I've got an m squared term that cancels an n squared term, and we get out our expected exponential decay. So it's really there, and it was really right. And it was essential that we had those n's in the master equation. If you instead said the rate of going from n particles down to n minus 1 particles went like lambda instead of n lambda, you get down here and you'd have minus lambda. You wouldn't have a row. Okay? So what you think of as exponential decay is each particle having its own decay rate and ignoring every other particle around it. And that's exactly what we have to build in the master equation, but that brings in some n's. Any questions? I'm either being too clear or... Okay, a plus a goes to 0. Again, 0 dimensions, one lattice site. We can only take steps down of increments of 2. There are n choose 2 ways to pick a pair out of my n sites. So I get, instead of an n, I get an n choose 2, but I've absorbed a 2 into my lambda. So we get probability flying in from being occupied n plus 2, and we get both of those factors in. That's just rate when n is n plus 2. And then we have a loss term as such. Make sense? Okay, that's going to be our, on each lattice site, that's exactly what we're going to put in for the a plus a goes to 0 reaction. Then we just need to compute. How do we do that? Well, let's first just get a hop, okay? Let's hop from 1 to 2. So now we've expanded our universe to 2 lattice sites. We're going to go from some pair of occupations n1, n2 to some other pair m1, m2. And in this case, it's going from 4, 1 to 3, 2. And of course, you can see how that would happen. One of these 4 particles chose to hop here. Each particle is hopping with the rate gamma, so the overall rate is 4 gamma, because any one of those 4 could have been the one that did it. All right? So, in general, we get an n1 gamma, right? Because it's any one of these n1 particles that's going to do the hop for us. And that's the only non-zero transition, and then the m's have to follow this. And 1 went down, 1 and m2 and m. So you throw that in the master equation, you get something like this. Gain term, loss term. Okay, that's a hop. I'm going to skip and a jump or whatever the buses are called. Okay, so what if we want to do a one-dimensional chain? Okay, one-dimensional chain. So now I can have hops to the right, I can have hops to the left. So the top row would be, okay, first of all, this sum goes over ij nearest neighbors. If you think of something like a square lattice, you're summing over bonds, right? Because each bond identifies an ij pair that are nearest neighbors. And then for that ij pair, you could have a hop from I to j, So you'd have a gain term where I had been occupied by one more, right? So you have a loss term. And then here's the reverse. J to I. Okay. You might say that doesn't look like diffusion. Well, similarly, we define rho of x of t. We pick a particular site I in some overall states. Now our I was a discrete lattice of integers. So to get to a physical length, we need to multiply by some lattice constant. So let x be I times the lattice spacing. And if you take delta x small enough, this indeed goes to the diffusion equation by a very similar technique to what we did for the exponential decay, and that's one of your homework problems to show that that indeed works. And the diffusion constant comes out, it's related to the hopping rate and the hopping distance. No real surprises there. Okay, so here we are. We're ready to define our model. Here is the master equation. And I should say one more thing about that diffusion. Let me back up. I didn't say anything about what dimension I was in. And the picture is one-dimensional. But that sum for diffusion actually works in any dimension. Yeah, so these ij neighbors could be bonds on a 2D lattice, 3D lattice, whatever. I will say, this exact relation with the coefficient of 1 here was assuming a hypercubic lattice. So square, cubic, whatever you call it, 4 dimensions, and so on. If you had some other kind of lattice, you get some other prefactor there. But otherwise, everything goes through the same. So, here we are. Here's our general hypercubic lattice. Here's the diffusion. Here's the reaction. This goes over all ij neighbors. This is over all sites. And we needed our initial conditions. This represents Poisson initial conditions, where you have an average occupation number of n naught. That's what n naught will mean this one. So great. We've defined our model. You could be given this as a research project. You need to solve this. And your first reaction when you look at that would be to say, yeah. I mean, there's all these n's. There's n squared. They've got nonlinear terms. It's pretty messy. However, if you're so read there, your first reaction when you look at that is say, oh, you need to give a generating function. And that's exactly what we're going to do. And that's really what the joy representation is about. So, let's see what this is. Bear with me a minute. It's not going to look like a generating function for a couple of slides. We're going to, because we want to, introduce a creation operator and an annihilation operator on each lattice set. Okay, why? Well, I hope to motivate that. These are, you may be familiar with, the quantum harmonic oscillator. There, you have raising and lowering operators, right? What are you creating? You're creating a little more energy, or losing energy when you step down. But they obey these canonical commutation relations. More generally, this is called a clock space, and it was an important development in trying to turn non-relativistic quantum mechanics into relativistic quantum mechanics when we realized that we can't conserve particle number in any kind of relativistic theory. So we had to write down something that generalized the normal Hilbert space for one particle to allow for pair creation, annihilation, all those sorts of things. So in that context, they're called creation and annihilation operators. And the key point is they're just some operators, and this is what they obey. That's all we really need. That's all they are, is that. Then we're going to choose to call the state of zero particles this thing. Just made it up. Getting back to zero particles. Now, the annihilation operator, as its name would suggest, when it acts on zero particles and tries to take it to minus one particles, fails, right? Because he's zero. So that really defines this. We can represent a state of n particles by acting n times with the creation operator on that vacuum. Steps it up from 0 up to n. Those of you who are really good at your quantum mechanics might object and you think I need a 1 over square root of n factorial. Well, we're using a different normalization here. The reason we're using different normalization is that probability in quantum mechanics comes from having, normalization has something to do with probability. Here, normalization has nothing to do with probability. We get our probability a different way. So we're free to work with non-normalized states, and it will make a lot of our expressions simpler. So we do. For this state, if I act one more A dagger on it, well, I just go to n plus 1. If I act on it with an annihilation operator, so you're used to some square roots here. Well, what square root? You act with an annihilation operator, you lower it 1, and you get a factor of n in front. in spite of the normalization difference, of course, A dagger A is still the number operator. These states are eigenstates of the combination A dagger A with eigenvalue n. That doesn't depend on normalization. Now, what if Sid's back there thinking, you just need a z to the n. What are you doing all this for? And, well, let me just comment on that. If this is z to the n, right, and my A dagger is just z, then of course this is z to the n plus 1. Right? What is the operator, if this is z, what is the operator that commutes with z to give you 1? It's d by dz. Okay? For sure, yeah, you can do that. And you can do everything I'm about to write down with that pair of operators. What I would call that a specific representation of the operators. I don't want to care about what the representation is. I just want them to have this property. However you get them to have that property, it's fine with me. Actually, later I will, but right now I don't. Now, that was all sort of one lattice site. If I have multiple lattice sites, well, I actually have to introduce a pair of operators at every single lattice site. Then, my general configuration, which is defined by n1, n2, I have to take a product over all lattice sites, and in each site, I've got to act with the appropriate number of A daggers. Okay? The key point here is, this is a one-to-one mapping. I still haven't really motivated why this is useful or interesting, but you can certainly believe that given any set of occupation numbers, I can construct this state, and vice versa. Now, it gets a little more interesting. I can take that whole probability distribution at time t and pack it into a box space state. So these are block operators in a box space. And now it looks a bit more like a generating function, right? I mean, here's z to the n. And so we've encoded all the information into this state in a way that we can retrieve it, which you do with generating functions. But here's where it starts to become useful. We can rewrite our master equation in the Schrodinger-like form. That's sort of nice and simple. What does H look like? And I'm going to derive this, but let me first show you. Here it is. That same master equation that took the whole page to show you is this. Plugged into here. There's no n's in sight. Okay? The combinatorics work out exactly right when you act with these. This is the diffusion term, by the way, and this is the annihilation term for A plus A goes to 0. And when you act on these combinations on your state here, you actually reproduce exactly all of those sums over p's that we had written down before. This is nice in a lot of ways. One way is that I can solve that equation. This is going back to kindergarten. Down in Abraham, I can solve the first order differential equation like that. That's a formal solution. I have to give it some meaning, but we can at least write it down, and that's going to be very useful. But where did I get this from? Why does diffusion come out to be this, and why does annihilation come out to be that? Let's work through that. And you might want to, I'll back up a second. Recall these are what you need to have in mind. If I act with A dagger, it just bumps me up the state. If I act with A, it bumps me down the state and gives me a factor of n. Okay, so let's just go back to a single lattice site. Here was our master equation for A plus A goes to 0. Same thing we saw before. Now we're going to multiply both sides of the equation by this box state and sum over all n. Well, p times n summed over n is exactly what our phi t is. So that's what the left-hand side is. The right-hand side, I think I've just literally done what it said in words. I've multiplied by n and summed over. Okay? But now I've highlighted a few terms. Okay, yeah. That's right. Now, look at the blue here. That's the same thing as if I acted 2 A's, the annihilation operator, on n plus 2. The first one's going to bring me down a factor of n plus 2 and lower it to n plus 1. The second one's going to bring a factor of n plus 1, turn it into n. So this thing is exactly the same as that thing. So 1, I've gotten rid of the n's in favor of these operators. And 2, this state nicely matches this. So I've got a phi sitting there. Right? Sum over pn plus 2, n plus 2, well, that's phi. And you might worry, what about when n is 0 or 1? Well, those are, when the A out here acts on those, it's going to pull over in. So when the state's 0 or 1, I should say. Now over here, similar thing happened. Well, a somewhat different thing happens. I need to get back to state n. Okay. So if I act twice with my A, I get the nice factors I want. I get an n at state n minus 1, and then I get an n minus 1, state n minus 2. Then I've got to act with 2A daggers to get it back up. Okay? So this one just requires two annihilation operators. This one requires two creation, two annihilation operators. So here I've just factored them out front. And now I've identified my state phi. And so now I've identified this, just like this, identified this as the Hamiltonian for that one process. Yeah.
Commutation matters. How did you decide the order?
Commutation does matter, so that order has to be the order. I decided it by just checking that these matched each other. Okay.
So it's just by construction.
Yeah. Yeah, you can't make any other combination of A daggers and A daggers on this state that are going to give you that. It's unique.
So A dagger and
just makes it n plus 1.
There's no factor.
There's no factor.
It's because you're missing a square on the A.
Because they have an extra square root, yeah.
Yeah, so that's just that order actually comes out of your choice of normalization.
No, actually not. If I normalize this differently and this differently, they'd still be equal. Yeah. You just have a lot of extra messy terms that were on both sides of the equation. Another exercise. I recommend working through that.
It might help you to think of the A dagger as PDC. I'm sorry, A dagger is Z and A is PDC. So if you differentiate Z twice, you get nn minus 1. You multiply by Z again, you choose the power back up there. Okay, so if you make it any other way, it would not be nn minus 1. I think of it as PDC is much easier.
If you want, yeah, I mean, if that helps, think of this as the derivative, think of this as the Z, and this is just Z to the n. And it's only Z to the n with our normalization, not quantum mechanical. So it would be Z to the n over n factorial square root with this quantum one. Okay? So, we got that one. That was, I'll back it up.
I think if there's, people have some experience with real many-body theory. If you look at that Hamiltonian, it's kind of a field.
Yeah, absolutely.
Feeling, right?
It opens up techniques.
You can almost write it, but I also mean you can almost write it by construction.
That's a couple slides ahead of me. We'll get there. Yes, that's an important point. I'm going through a lot of formalism, okay? When I go to solve a new problem in this area, I don't go and repeat all this. I can go right to the end because it's that simple. It's that direct. Once you understand the mapping, you tell me the process, I can write down the field theory. It's okay, and how many other people do it. The hop from site 1 to site 2. We're not trying to do diffusion, just one hop in our two-site universe. Here was the master equation. We're going to multiply over this two-site state, right, that was created by A1 daggers and A2 daggers. And, okay, so there's a brace here, right? This is all we've done in the first step is multiply by N1, N2, and sum, right? So this right-hand side is just the master equation with an N1, N2, and sum. Okay. Now our goal is to get that into something in terms of the state phi. So let's focus on the blue. If I act here, I get N1 plus 1 turns into N1. That's good. And I get a factor of N1 plus 1. That's good. I need to turn N2 minus 1 into N2. I act with a dagger. And I get N2. Why did I want this? Why did I want to have an N2 minus 1 here? Because it matches this. And that gets me the state phi. Now logic working. This one's a little simpler. I want to get exactly the same state. That is, I want these match already. So I just act with the number operator. Okay. So at this point, at this stage, I have my states matching my p's. Okay. So that means I can just bring these operators out front, and I have the state phi. So here it is: A2 dagger minus A1 dagger, A1 on state phi. That's a hop from 1 to 2. There it is again. It's just what we wrote down. We want to allow the reverse hop. We just add the same term in with 1 and 2 spot. Right, if I take this again, but I make this 2 minus 1, well, I'll get a little sign. Turns into that. Okay, so this now allows hops back and forth at equal rates between sites 1 and 2, and now we can generalize to any lattice with nearest neighbor hops. Phi and j. Okay? So that's the Doi diffusion term. And we've actually now derived the Dorian representation for time. Okay. We got this, we got that. So there's our master equation. I can write that down a lot easier than I can write down the master equation. I have to think to write down the master equation. I don't have to think to write this down. And I'll tell you how. Just a quick aside, what if I have more than one species, right? Up to now we've only talked about one kind of particle. Well, fine, I need two sets of occupation numbers. The occupation numbers for my A's, occupation numbers for my B's. Give me C's, I need a third set, and so on. And then, sort of in an intuitive way, you just also need another pair of creation and annihilation operators. These are, I should say, all mutually commuting. So A at side I and A dagger at side I don't commute, right? But the ones on different sides all commute. And all A's commute with all B's and vice versa. Vice versa. So then you make your state by sort of the obvious way, some overall configurations create the appropriate state. It's just a sort of higher dimensional generating function. Okay, here's how you make the right Hamiltonians without going through all that. Every process that you're going to write down, all right, I kind of skipped an important point. Early on, we talked about, with the plain old exponential decay, that it was a crucial point that all particles acted independently. That's why we ended up with no n's left over when we got to the Dwight Hamiltonian. Okay. For any model where that's going to be the case, the Dwight Hamiltonian is going to simplify for you. It's going to give you a master equation that has no factors of n. Okay. So that's one of the morals of the story. Box space is about independent particles. Okay. Now, if we've got some process, a hop, decay, whatever, it has the form of. Think about the master equation, right? We have a gain and a loss term. What that turns into in the Dwight Hamiltonian is, of course, you've got some rate. You've got reactance minus reaction. Now, let me explain that. Reactance. Those are the things going into, right? A plus A goes to 0, or A plus B goes to C, or whatever. And for those, all you do is write down a creation and an annihilation operator for each reactant, but you do them normal ordered. And normal ordered means all the A's on one side, all the A daggers on the other. So, as an example, A plus A goes to 0. Here is the reactance term. I've got two reactants, so I need two A daggers and two A's. Notice that this reaction is the same thing, right? Because it's the same thing. I have two reactants, two A daggers, two A's. Here is a birth process, or branching process. I've only got one reactant, so I have one A dagger, one A. Right? A plus B, well, I need an A dagger and a B dagger, and then I need an A and a B. If I hop from 1 to 2, I need to have a particle on 1 to do the hop. So that's my reactance. Okay. Now the second term is the reaction. That's more like writing down the actual reaction. So A plus A goes to 0 says, well, you take two A's away. I need two annihilation operators. A plus A goes to A says, well, I take two A's away and I bring one back. A goes to A plus A, I take one away, A away, I bring two back, and so forth. That's it. It will always work out exactly like that for independent particles. Yeah.
Always in normal ordering.
Always normal order. And yep. And you can, question about.
Yeah, maybe I just guessed it because you're done. But why, when you write A dagger A square, why not just write A?
Because it's not going to be the same thing. It's important. If you think about what this looks like in the master equation, right? It needed a factor something like n plus 1 times n. To know how many pairs there were possible when there were n plus 1 sites.
Yeah.
Okay? So you need two A's to get you those two factors of n.
Okay.
But then to match what you want as far as the state, you have to step back up one.
Okay.
That's how it comes about. So this, I didn't actually assign this, but I recommend just make up some reaction. A plus B goes to 2C or whatever, and see if you can write down. Actually, I did assign a problem like that. Write down the Dwight Hamiltonian, and don't do it by working out the master equation first. Just go straight to this. Yeah.
Usually, what you mean by independent particles are reacting with each other, so they're not really independent.
Right, but they're all reacting with each other identically. Independent is not a good word. Identical is what I'm trying to say. What's that?
Indistinguishable.
Indistinguishable. And also another quick word about quantum mechanics. Non-relativistic quantum mechanics doesn't speak to whether particles are indistinguishable or not. Because you have one particle, right? You have two particles, right? You have to go to, well, I guess if you go to two-state wave functions or two-particle wave functions, they didn't have to come that way, right? It's an experimental fact that we have bosons and fermions. You can write down all the rules for Coherent equation and Hilbert space with distinguishable particles. It's just not the way nature is. Okay? So the box space was an actual way to put in the indistinguishability of quantum particles, and that's why it arose in that context. But that's what it's about. It's about indistinguishability. So even though we're doing classical mechanics, the box space is still useful. We're not doing classical mechanics. I mean, you know, classical thermodynamics. Okay, big issue that I've ignored up to now. How are you going to measure anything? Okay, well, let's go back to our original definition of the model and say we're going to want to calculate some quantity, A, it'll need to be a function of the occupation number, right? That's what determines what state we're in. So the way we would compute an average is we'd sum over all occupations, A times the probability. So we need to be able to do that, too. And so you might think, all right, fine, you know, quantum mechanics comes with expectation values. But let's remember that our state phi, which must be up here somewhere, here's one. Our state phi is already linear in the probabilities. If I take a phi here and a phi here, I'm getting things that are quadratic in the probabilities, and that's clearly not kind of averaging I want to do. Okay? So that's not what you do. What you need is this projection state, which is defined as follows. You take the dual vacuum, and you act on it from acting to the left with the exponential of the annihilation operator on each particle. What's the point of that? Well, the real point of that is that it has these properties. So first of all, you can check pretty directly that if I hit this on the right with the vacuum state, that only, so the way you define exponentials of operators is in terms of their Taylor expansion. So this is 1 plus the sum plus the sum squared of 2 and so forth. Well, anytime I've got any A's in there, I'm not going to get anything. The only thing that survives here is the 1. Okay? It's a little more work to show that if I act with A dagger to the left, this is actually an eigenstate. There is a nice result that if I act A on some function of A dagger, it's like taking a derivative. And this is the same thing, just in the dual vector space. Okay, so this is a dagger acting. It's like taking a derivative.
This is also a coherent state.
Yeah. Again, you're 2 slides ahead of me. Right, they're coherent state eigenstates. And if you put these two together, you get this property. Namely, I can start with a vacuum state. I can act on it with any number of A daggers to get to here. But if I instead think of those A daggers as acting to the left, and just keep giving me 1, 1, 1, 1, 1, I'm finally down to that. Okay? So, this is really what we want. We want to be able to pack everything into our box space state, but then we want to, excuse me, we want to be able to extract out of that this sum, and that's exactly what the projection state does. True.
How do you define these draw vectors? I mean, a conjugate space.
Yeah, but with that we do in the conventional way. The conjugate of A dagger is A, the conjugate of A is A dagger.
There's no process normalization or...
No. So I'll get to the normalization actually pretty soon, but the key point again is we're getting probability a completely different way than you do in quantum mechanics. So that's why we can now worry about it. Now, what does this turn into? Well, I can take my function, and I can imagine a Taylor expansion of this in terms of all those little n's. I replace each of those n's with a number operator, and that creates this A hat operator. If that acts on this state, these are eigenstates of all the number operators, so all they do is, when they act, is convert back into the number. So, this thing reproduces that. May or may not be honest, but and then I just threw in the formal solution here. If we want to, we can relate this average at time t to an average of A times the time evolution operator with the state at 0. And if we do go back and map our Poisson initial conditions, which is what we wrote down earlier, into this formalism, they look like that. So this is, give me some quantity A I want to calculate. I'll turn it into this operator, and I'll try to average this thing, and that's how you solve the problem, if you can do that average. Okay, any questions? Yeah.
What about the equation of motion for A?
What about the
equation of motion for A?
Wait, which A? This A?
Yeah.
I didn't put explicit time dependence in there. Is that what you mean? Or?
No, I mean, can you get it as the same as in quantum mechanics from a commutator with the...
No. Good question. I never thought about that. You never thought about that?
What was the question?
The question is, you can write down the dynamics of, and sort of a commutator relation. Yeah. I think it doesn't work out. I think that really reluctant.
You see that in the last slide. You expect the time derivative of A of t, you're just putting down an h inside. That's no commutator. And that's again because totally different algebraic structure.
There's no left part.
We're not really doing quantum mechanics, right? And the key point is to this projection state thing too. If I were actually doing quantum mechanical averages the normal way, I could get quantum interference effects. I could get coherence things like that. But that can't be in there, right? That wasn't in the model. So this projection state sort of preserves the classical behavior that we expect.
So the question was whether there's a Heisenberg equation in motion.
Yeah, and I'm quite sure there isn't. I haven't really thought about it.
It's not either H is not on both sides.
Yes, yeah.
And you might be helpful to say that unlike quantum mechanics, H is not Hermitian or symmetric. If it's symmetric and Hermitian, then the problem is more intense.
Okay, yes, indeed. Actually, diffusion is Hermitian, but one could argue diffusion is more intense. Okay.
I'm sorry.
All right. So let's go. We talked a while about probability normalization. So let's get that clear. So this thing, we would assume in our classical model we started with something normalized. So let's see if that works. That is to say, if I take the identity operator and I act it here, I better get 1. The average of 1 better be 1. So here's my state, phi of 0. The identity operator is acted and disappeared. But remember that the overlap of P with any state n at all is 1. So this and this just change the factor of 1, and indeed I get probability. What about conservation? Okay, that just says my initial state in this formalism works out. That turns into a condition on H, but it's not hermeticity. So again, if I evolve to time t and then I average 1, I better get 1. So I evolve to time t. Now here's the way you do exponential and operators, the Taylor expansion. The first term indeed is 1. So that 1 in t gives me 1. So all those other terms had better vanish. And that is our condition for probability conservation, is that H, acting to the left, needs to be 0. Has to annihilate the projection state. Okay.
If H isn't Hermitian, how can it act to the left?
Hermitian just says H acting to the left is the same as H acting well. So if I have H or any operator acting to the right on some state, then the dual of that is the Hermitian conjugate. I mean, hermeticity says that this is in fact the same operator again. Okay. So
the answer is H would not annihilate
P. Yes. Yes. Thank you. This is not 0. If H is not Hermitian. I know, we're so used to hermeticity. There's sort of a joke about the way mathematicians view physicists. And the mathematician was giving a talk and saying, as all physicists know, all operators are Hermitian.
Well, can you finish that last slide? There's some.
Thank you. There was a point there. So first of all, H need not be Hermitian. This property, remember that A dagger acting to the left, this was an eigenstate with eigenvalue 1. That is, A dagger acting left just gave me back the state. So one way to view this property, one quick way to scan your Hamiltonian and see if you made a mistake, is if you replace all the dagger operators with 1, it better vanish. If you go back to that general thing we wrote down in terms of reactance minus reaction, you can see that following that recipe, you will always get H to vanish because it comes from a valid mass transfer. Okay? All right, so we got to the Dewey representation in the quantum mechanics. We got 20 minutes left. All right, let's turn it into a field theory. Yeah, enough said. So we all mentioned coherent states. Here they are. What are they? They're eigenstates of the annihilation operator. So if A acts on state phi, it comes back to eigenvalue phi. Phi is a general complex number, anything I want it to be. And I construct the state as such. This is a normalization factor that, it's just part of the coherent state. This, you can see, I've got an exponential of the A dagger. So if an A acting on that is like a derivative, it's going to give me back the exponential as well. If I take the conjugate of that, then A dagger acting to the left gives me phi star, just the usual rules of dual space. You can show that for two such states, with phi 1 and phi 2, you have the overlap relation. These are the normalization constants, and you get this thing. It's not directly obvious, but you can show that. Basically, the only thing that survives are when you have equal numbers of A daggers from this expansion and A's from the dual expansion. Okay, what we're going to do with this, the usual way you make a field theory out of quantum Hamiltonian is, well, it's on the next slide, but you imagine evolving it by that e to the h hat t, but you break the evolution up into many tiny steps, and then between each step you want to insert an identity operator that's judiciously chosen to do something nice for you. And that's what we're going to do now, is construct a nice identity operator. So normalized states, this factor wouldn't be here. Whenever I have an orthonormal basis, the identity operator is just given by this thing. If you haven't seen something like that, just think of this as, Euclidean spatial vector. This is take I hat dot your vector, now multiplied by I hat. Sum those all up, you get back your vector. We don't have normalized states, so now we get that in there. We've tucked it away somewhere where it didn't clutter a lot of earlier expressions. It's not a big step to go from here to here. I can do a double sum if I throw in a Kronecker delta function. What's interesting is that this thing can now be shown to be an integral over the complex phi index of the coherent states. Okay, that relies on this resolution for the Kronecker delta function. I should add this d2 phi means we're talking about a complex variable. It's a d real part of phi, d imaginary part of phi. So it's an integral over the whole complex plane. It's not a contour or anything. One interesting thing, this is not, and notice the pi here, this is essentially an overcomplete basis, right? So I don't have a 1 there, I have a pi there. But it's fine, it still is, it gives me an identity operator. So I can still insert it as well. I will make one observation. If you had instead wanted to use the z and d by dz representation for the operators, you can still get to here and you can still make an identity operator. Here's a bunch of d by dz's and here's a bunch of z's. You do have to, at this point, pick a contour to integrate through to make it all work out. And that gets you to the same field theory. And that's called the Bargmann representation, as opposed to this being the coherent state representation. Mathematically, it's really identical. This is, again, in my view anyway, the minimal description. This is the most simple and straightforward way to get there. You don't have to do any contour integral. Okay, so if I'm given some Hamiltonian, and here's my formal solution, this is what I was saying before, we break it up into tiny steps, okay? And then between each of those, so I imagine this now is a series of products. This is some integer, big integer. And I'm going to insert one of these identities between each successive, so it looks like here. So here's a delta t time step, and then here's one identity. Here was a different delta t time step, here was the identity before it, and so forth. The complex numbers at each insertion are distinct, right? So this integration is over a whole huge number of complex numbers. to dissect this, let's focus on a single matrix element. So now I can look at this as a unit, right? Because this is going to be, after all, a product of matrix elements. So here it is down here. Oh, I picked this one. Okay? So here it is down here. If I think about this thing, it's normal ordered, right? So all the A's in it can act to the right. This is an eigenstate. So they're going to all act to the right and get replaced by phi's at t plus t minus delta t. All the A daggers here are going to act to the left and get replaced by phi stars at t. And so at that point, this thing is just a number, and I can bring it out. Right? Now, let's see, what did I do next? Okay, hey, we can use our useful overlap relation that we've written down before. Here it is. It's the overlap of this star with that, and then minus half of this mod square and half of that mod square. And what did I do on the next line? I think I cheated.
Yeah, there's some chance.
Yeah, okay. So here's the key point. Think about, there's going to be a series of these, right? So I can take this half of this thing, and I can give it to the one down that way, right? And upstream, I can take that extra half from the t to t plus delta t1. So this could, by just doing that everywhere, I could turn this into phi star of t, phi of t minus delta t, minus phi star of t, phi of t. And the point is that becomes phi star of t to leading order time derivative. That may or may not be obvious. That's, the key point here is that we're handing that one off downstream, and we're getting the identical half of that first. Yeah.
Is there, I mean, the notation suggests an approximation from line 1 to 2.
1 to 2, no, there isn't.
Well, you squiggle.
Oh, yes, I did. Up here I did. Because I wanted to not distinguish that these are, since this is already ordered delta t, I can throw away the difference between those two.
Oh, I see, yeah. Okay. So it's still lowest order in delta t?
Yes, yes. And that's valid because in this expression, I'm going to take a limit of delta t goes to 0.
Right.
Okay, so if we string those together, let me back you up here. We had some delta t's here, right? We had phi star d by dt of phi, and we had the Hamiltonian. So if I string a bunch of those together, it's a product of a bunch of those things. So that's the exponential of a sum. And here they are, phi star derivative, there's the h's. Okay? So that's what comes out of that. Then I have all those huge number of my integrations, right? And all those pi's. And I hide my ignorance in a script D. And I'm not going to worry about it. We'll normalize at the end of the day. So here it is. It's a nice, easy way to resolve that operator. And you do it for the same reasons you do it in quantum field theory, namely you want to get rid of operators. In quantum field theory, you want to be able to treat time and space on an equal footing because to make something relativistic, it needs to be. And that is a problem in non-relativistic quantum mechanics because space is an operator and time isn't. So you get rid of the operator nature of space. Well, here we just got rid of the operator nature of and here we are. There's our ignorance. If I go to multiple lattice sites, nothing really changes. I just get a lot of these functions to integrate over and a lot of arguments for that. And here's our basic so as is called an action. And notice it appears in the exponential there without any i's, without any h bars. And so that's our path interval. Okay? Now I haven't taken a continuum limit of the lattice yet. I guess we'll get to that in a second. I think we're doing it right. Okay, so our averages, remember when we wanted to compute something, this was how we compute it. You map that through, and it turns into, you just need to, this is a function of A operators only. I should add, so our A hat was A of n goes to A dagger A, right? But then at the end of the day, I can normal order it. Okay? It won't come normal ordered, like an n squared term will be A dagger A dagger A. But I can choose to normal order it. And at that point, I can act all the A daggers to the left and get rid of them. Key point being, I can make any operator I want out of annihilation. And then I just replace the annihilation operator with phi of t a lot of steps, but again, you don't do this every time. Right? Once we get to the endpoint, we've got what we need. Now, here's an interesting thing, though. So there's this normalization. By the way, that's where my ignorance was hidden. I would just compute the same functional integral, however I'm going to do it, with A missing, and that's my normalization factor. But now the projection state rears its ugly head, and it needed to be part of that averaging, because it was there after all. And so it shows up as this phi at t. Notice t is the final time for this particular piece of the action. So that definitely comes directly from the projection state. I also have my Poisson initial conditions, which give me a term like this. That's not bad. I want to have that. I mean, my answers need to depend on M naught somehow.
So what does that come from?
The Poisson initial condition. So we kind of talked about what happens down the chain of all those insertions in the identity. But waiting over here at one end is an initial state. Okay, right? It's a coherent state. Okay. And so when there's actually a few i's to dot and t's to cross. You actually have to do that a little carefully, but you get to here. But a nice thing happens if you do a field shift. So we're going to trade phi star for 1 plus phi tilde. And the magic happens in this term. So here's phi star. So one term looks just like what I had before, which is phi tilde, right? The second one. So the first one is just an integral of a derivative. So it gives me phi of t minus phi of 0. And notice this phi of t is exactly what I need to cancel that. The field shift gets rid of your projection state for you. You can actually do this shift back at the operator level too if you want. It's arbitrary whether you do it before or after. You can turn the projection state into a magnet. I prefer this one, but it doesn't matter. This turns out not to do anything. It sits over here and becomes another term at t equals 0. But because it's an annihilation output, well, it's a phi and not a phi tilde, it has no effect. And again, that's a little bit of work to show, which I'm not going to go into. But that means in our Hamiltonian, we're going to want to map to where we had phi star before. We're going to want to replace it with 1 plus phi tilde. That's all we have to do. It helps us avoid having to do some infinite expansion of this thing that, among other things, has no parameter in front of it to be small. Okay, this all looks very formal, okay? And like I said, we've done a lot of math. We haven't calculated a thing. Let's see if we can at least handle, a good old linear problem. If we took the diffusion part and mapped it in, the Hamiltonian, this comes from those overlaps. This comes from the Hamiltonian. It had some A's, AI minus AJ, and some A daggers. And so those acted to the right and gave me phi's, and these acted to the left and gave me phi stars. When I did the field shift, it did nothing. The shift canceled. So there it is. Now, if I do take a continuum limit, this is basically a derivative, right? And this is a derivative. All right, that doesn't look too bad. I'm now allowing this, I'm taking the whole thing and integrating over time and space. So for my initial term, I threw in a delta function. I'm not worried about halves, right? But the whole thing there. Go to epsilon before 3. Now I can do an integration by parts on this term, and I get something that's looking a lot like the diffusion operator. And that's in the action. Now that whole thing, remember, is up in the exponent. Notice it's linear in phi tilde. So I can think of it as e to the phi tilde times something, and this is effectively a delta function. And what is it, a delta function? Or equivalently, I can calculate an extremum. This is what I get, and that is the diffusion equation. Now, you may not usually see that with the M naught delta t, but what you imagine is that this applies for all time, but the initial condition is that t equals 0. So you go from having nothing to flip, now you go up to M naught, and then you go to diffusion. Yeah?
Is the only assumption so far that there's a continuum to the left? Is that the only assumption?
I did that to make this look more like the diffusion equation. I could have not made that assumption. I could get down here with the lattice derivative. So the continuum limit is, that's one nice thing about this formalism, the continuum limit is actually very clean. You can do it earlier, you can do it later, and there's not really any pathology with it. Well, I guess I should qualify that too. When it's a linear problem like diffusion, there's no pathology.
quickly.
Yes.
Do you have a direct relation between this phi and the moments you have written at the beginning? Coming from the master?
Fairly direct. For example, that's an important question. Thank you. I can ask what's my average of n I in the classical model, and that is indeed the average of phi. Higher moments are slightly more complicated, and I'm a little short on time. I'll talk about it in a later lecture. But yes, you can relate all the moments of these to moments of those. Absolutely. Okay. If we want to do the same for the reaction part, we have this 1 minus a dagger squared, a squared. So we're doing 2 steps here. One, I guess we're not. We've already turned those into phi's. Now we're doing the field shift, and that gets us to here. Notice there's no terms that are 0th order in phi tilde. There will never be terms 0th order in phi tilde because that's where probability conservation comes in. That's like taking a dagger to 1. That is to be Hamiltonian to 0. Okay, replace my lambda with something that, so I went from a sum to an integral, so I factored in a little volume element. So here we are. This is the action for k plus a goes to 0 field theory. After a whole hour of math, we're actually ready to start a calculation, if you like. That's nearly the stopping point. Let me just point out, here's diffusion, here's the reaction, here's the Poisson initial conditions. It really boils down to that. There's an interesting, let me actually put the lights on for just a second. So Downing was talking about these reaction diffusion equations, and we're double checking. If I were going to write down the reaction diffusion equation for this model, I would probably write something like minus something a squared, and, well, that's simply the rate equation. I forgot the diffusion. We'll put it here. And then I would say, well, maybe I need some noise. And what kind of noise should I expect? Well, here's my Gaussian white noise. It's probably going to be multiplicative because as I run out of particles, the A and phi are the same thing. Sorry. So I run out of particles, my fluctuations go away, right? So some kind of factor like that, and then there would be some unknown prefactor, and then the problem here, of course, with this kind of reaction, there's no back reaction. We're nowhere near detailed balance. We've got nothing the least bit thermal. So I just make up something and maybe put it in. Well, and as Danny said, he doesn't like that. We can actually get there. Not for every case, but for the A plus A case we can. And the trick is the following. We can, when we did the diffusion equation, if we have something linear as phi tilde, we could just get a delta function out. The reason we can't do that with the reaction is because we have this quadratic term. Okay, well, I can do this complete the square trick, right? If I introduce a new field, eta, that has a Gaussian form here, but it's got a shift, then if I complete that square, I end up getting, I can show that that's proportional to that. And you can go through the steps of that if you want. So that means my integration over all possible fields now also has to include this auxiliary field that I've introduced. But if I look at what I have in the action, everything is now linear again in phi tilde. So I've got a delta function again, and it gives me this equation. This thing has to be averaged against that. That's exactly what Udo was talking about this morning. That's the way you represent Gaussian white noise. So here we are. There's our Gaussian white noise. There's phi. Hey, I learned the prefactor. And then I got an I. The correlator, you can absorb the I into eta if you want, if you don't like it there, but then the correlator is negative. One way or another, you got something a little counterintuitive here. Remember, phi is complex. The average of phi is real. The average of phi is the density. But this is a nonlinear equation coupling real parts and imaginary parts of phi. And if you don't have that I in the noise, it's not right. You don't get the right answer. So this is a cautionary tale for anybody doing classical stochastic particle models where you have these identical particles. I would highly recommend going through the steps to derive the stochastic PDE before you just write this down with something real here and making some guess for this. Okay? And this is really a rare bird. This is a problem where we can actually get to a Langevin equation without an assumption. We're far from equilibrium, we don't have detail balance, we don't have temperature, and we can get a Langevin equation. Langevin equations. Okay.
I have a question.
Yes?
Why is n pi average? Shouldn't you have an operator average there?
Well, there's
A average, right? I think it should be A average.
It's a three-step process, right? So this is, those all are the same. This is in the classical particle world, this is in the Roy representation world, this is in the field theory world. And for the one-point function, they're all the same. The two-point function is a little bit, they're relations.
So this notion of getting the Langevin equation is just the inverse of the Yang-Zinzi dominance.
Yeah, we do it backwards. Exactly. So what he's referring to, there's a well-developed formalism for when you start with something like this to get to something like, well, the action was on the previous slide. But in those kinds of cases, you're usually assuming those Langevin forms from some phenomenology. We didn't have to do phenomenology. That's what's really unique about this method. Yeah, other questions? Yeah, no.
You have multiplicative knowledge. You get a rule for each versus Stochanovich.
The rule for what?
Each versus Stochanovich.
Yeah, actually there's an important, so early on I had this phi of t and phi star of t plus delta t, and you have to be very careful to do, if you're trying to do any simulation like that you do the time splitting in the right order. If you do it wrong, it totally messes up. So this is a kind of formal expression. There's some extra rules that come with it.
It's Ito-like. It's
Yes.
always disputed.
Sorry, I didn't answer your question.
What was the answer?
It's Ito.
Ito.
But and there's a real important, you see why from the mapping. You don't have to guess.
If
So,
you go back in your transparencies, there is a place where it is.
yeah. I was hand waving, but somewhere. Here. You could remember that, and if you swap those, it messes everything up. So that part is a little. So the spatial continuum limit is pretty well defined, at least for linear things. The time continuum limit is a little bit dodgy, like it always is. Okay, main summaries. Mapping to Doric representation, simplified the master equation, got rid of those ends. And what I said earlier, that this box space description is really not about quantum mechanics. It's about identical particles. We don't need to do anything with phenomenology. We just get to the field theory and, if we want to the stochastic PDE. There's no problem in having multiple species, long-range hops, levy flights, things like that, birth-death processes. You can do convective fields, all of these things. You can at least write down the action. What you can do from there varies. Here's an important caveat. We were talking about this H, so if you wanted to put in some interactions, you've got some random potential surface you're hopping around in. You've got to be careful. H is not about energy. H is about hopping rates. Okay? And if you think about a metropolis kind of algorithm, hopping rates are usually some exponential in the energy. Right? So it's going to be some exponential in H at best. So don't follow that trap. And this was the last moral, namely stochastic partial differential equations can be dangerous. Make sure you are working with the right one. I didn't give a single citation, I think, through all this, because it was kind of a background talk, but let me give you some references that may be useful. The Fox-based representation was introduced by Doi, I guess that's kind of obvious. Grasberger and Schreier also did a very nice extension of the formalism. Guidi was the first one to derive the field theory. He was using this Vargman representation. And if you want to learn about general path integral techniques, these are two excellent sources. Schulman, I'm very partial to. That's where I learned all this stuff. And it's just an excellent book. He's got a skill for not giving you extra information, so you get right to what you need to know. And then this was something I put up as background reading for the whole set of lectures. It's a review article we wrote recently that has also a lot of these details in it. And I'll take your questions.
Clarify how you take the average and what does brackets mean? Are you still multiplying by a few somewhere or not?
Well, each average means something different, but the That's what the first one means. That's the second one. And that's pi is 0. And this is so the whole point is we really step by step through showed you how one does those along the way, more or less.
Let's say from clear and stochastic. Could you give us a sense for when the field theory versus when it will not be?
That's a great question. That's the start of my next lecture. Field theory is particularly useful when you have essentially some criticality, some emergent scale invariance, because then you are going to try to do some kind of renormalization group analysis to uncover that, and we have a lot of techniques for doing renormalization group analysis in field theory. I would argue that it's also useful when you want to know what the noise is supposed to be in your stochastic PDE. Those are about the two uses I can think. Yeah?
Going back to one of your summary observation points, you said this could also be generalized to convective fields.
Yeah.
Can you say a little bit more about that? I mean, when you say it can be generalized, do you mean the Dvoy formalism? You mean the field theory?
The hardest part is to start back at the master equation level, but you can imagine your lattice being convective, right?
Okay, so similar to diffusion.
Yeah.
You would look at. Okay, all right, fine.
So can one start at the language equation to construct the phenomenology?
Sure, that's what somebody was asking about. There's a well-developed technique. So as long as this is Gaussian noise, you can replace this with some exponential of this thing and an extra average over that Gaussian field. And that's often a very useful thing to do. It gets you, when what you started with is a longitudinal phenomenology and you want to get to some field theory calculation, that's the way to go.
What is that approach called?
It's got a lot of names. What were you calling it?
Martin
Cigiaros, it's called. It depends on what side of the Atlantic you hail from. I'm not going to.
We wrote it down this morning, and from there it's just an additional step.
Yeah. The whole real trick is that completing the square of the field. So you work through that once and you see how it works.
I was going to ask, for the retrospective, there's some understanding of the nature of noise, nature fluctuations that this imaginary noise captures?
Yes, absolutely. Thanks for asking that. The key point, so remember this was the field theory for the A plus A goes to 0 reaction after all. The particles, when the rate equations don't work, anyway, so under certain conditions, I'm going to also argue that we can tell when this matters and when it doesn't. So we can show that for d greater than 2, this term can be ignored, and for d less than 2, it's there. But when d is less than 2, and when that term matters, your particles are very strongly anti-correlated. Diffusion is not managing to mix them because they're too effective at reacting. And if you put this in without the I, you can show that you would have positive correlations. You need the I in there to get negative correlations. It's a few steps to show that, but yeah, it absolutely needs to be there.
So which master equations cannot be turned into a field theory?
Well, anything that relies on the, first of all, there's things that can be turned into field theory and there's things that can be turned into useful field theory. So there are a lot of things that end up getting these exponentials of operators in the Hamiltonian. You write down the dynamic Ising model with some Robert dynamics. You can write down this field theory, but you're not going to go do much with it because it's going to involve a Hamiltonian that's an exponential of the operators. The only reason you can't do this is when you have particles that are not identical in some way. I mean, I guess if you had n particles that aren't identical, you could have n fields that have been as big. That's useless. So, for example, that original radioactive decay example, if instead of taking my rate n lambda for the transition down, I took the rate lambda, I can write down a Dwight Hamiltonian, but it doesn't simplify anything. It's got n's in it.
What's the relationship between correlation functions of the original particles and correlations of
Well, I keep trying to avoid that, but I guess I'll get into it. So if you start with some Ni, Nj average that you want to calculate, so the rule was you take the n's and replace them with A dagger. So I've got an AI dagger A, AJ dagger AJ, okay? And so I'm doing some kind of average of that. So that might be a little sloppiness. But I want to normal order that. So if I normal order that, I get AI dagger. See, I didn't want to do this. I'm going to mess it up before. AJ, AI plus or minus delta IJ. Let's see, which is it? Yeah.
So it's basically the
okay,
same.
So when I equals J, okay, then I pick up that extra 1. Right? Well, at this point, I can act all the A's to the left, so it's basically AI plus delta IJ, AI, AJ. So it actually involves a correlation function and a. Wait, I did something wrong. Something did wrong here. I don't see it.
It's AIAJ. That's the IJ.
AIAJ, yes. That's right. Thank you. So, I get the correlation function, sort of the thing you'd expect when I get this extra piece. And that matters in some situations. But it also says I can get the sort of correlation functions in terms of the 2-point and 1-point functions for the field theory. And in general, I can get the third order ones in terms of 3, 2, and 1. Yeah.
So for this one, n average, I need not take A dagger A, right? Because I have a P sitting on the left hand side anyway. I could just take A.
Yeah, for that one case, that they're really identical from the beginning.
And you're saying high correlations is not? Could I just
Right.
not write A and A?
Well, it goes back to where we got this relation for A average.
Well, because the identity between n and A and A.
So I needed this thing acting on that to, I need this to be an eigenstate of A hat at first. So it's an eigenstate if I mention some Taylor expansion of my function, A of the n, and there could be higher order than linear terms, and then for every one of those n's I replace it with an A dagger A, then when it acts to the right, it's going to get me back to the appropriate ends. But now it's not normal order, and then I have to do the normal order. We can talk later.
You only replace A's by 5s when they're normal order.
Yeah, so this gives us information about the configurations of the system, the locations of the particles, right?
They can, yeah.
Does it say anything about the currents in the system?
Sure. I mean, the current, if you're talking about a diffusive process, is going to be something like a derivative of the field, right? So in my third lecture, when I talk about some of the applications, one of the things you can do is set up A's and B's heading towards each other's currents, and we'll write down some things pretty describably.
Did we ever use the commutator law?
Yes. I'm sure we did.
In the sense that it seems like everything in the Hamilton, when you're constructing the Hamiltonian, it seemed to always follow in normal order. And it's essentially a classical system you started with. So what is the role of the commutator?
No, I'm going to blank, but they're absolutely essential. What's that?
Creation and relation.
Yeah. I mean, I was implicitly throwing in a lot of standard knowledge about dual vector spaces, and none of that would have worked if these were not non-Canadian operators. I'll have to think to give you a better answer, but
well, A dagger A being the number operator,
for example.
These guys being number operator eigenstates, all that relies on that configuration.
So one advantage you're saying is that you don't have like these phenomenological constants floating around, but in your lambda you have like 1 over the lattice spacing. That got lumped in there.
Sure. Well, that's an interesting question too. So I was saying something about when d is greater than 2, I can show that we don't need this term to describe the one term, and when d is less than 2, we're going to need that term. And when d is less than 2, the continuum limit to this nonlinear problem is a little problematic, and that's why we need the normalization, and we will be doing all that Tomorrow.
All right, let's continue our discussion informally outside of coffee and all that. And we convene in 5 minutes to 4, please, in 25 minutes.